And to do this, I'm going to use a couple tools. Stress analysis combined with the trend tracker that's only available in Simulation Professional and Simulation Premium. So my goal of the analysis is going to be to reduce the deflection of the handle of the spreader under 2 millimeters while keeping the mass at the same level or decreasing it. In addition, I want to be able to validate the size and strength of the welds holding the tube frame to the base of the spreader arm. So we have a model of the handle on its own, and I want to analyze this in two different fashions. The first study, I'm going to use a solid mesh, and I'm going to use bonded contacts to connect all my components. And actually I would like to apply this analysis to a model where I have the weld defined as a solid body. So I can actually duplicate this study and apply it to a different configuration of the model. And we see that we now have solids representing the fillet weld, and I need to apply the material properties. Apply that to all the bodies of my model, and we'll start out by assuming that everything is perfectly bonded, and then we're going to modify our contact sets such that they're a little more realistic. I do need to apply some fixtures, and I could use bolts to have a more accurate behavior at this location, but in this case I'm just looking at the deflection of the arm, and I'm not concerned specifically about what's happening near this fixture, so we can just fix the constraints. Then I need to apply a load to the handle, and by default we choose normal to our faces. We can see the loads are normal to the faces that we select, but I want to do this in a specific direction relative to plane 1. And we'll apply 500 newtons normal on the handle face. And then the way the model is set up currently, we're going to assume perfect bonding between all the faces that are initially in contact. And I can run my analysis. Now I want to keep track of how my design and contact changes are affecting the performance of the model, so I'm going to turn on our trend tracker. And what this is going to do is it's going to keep tabs on key sensors in the model, displacement, mass, and maximum stress, and it's also going to take a screen grab of each one of these results. But when this is actually welded, the ends of the tubes aren't going to be bonded, so I'm going to set up specific contact sets. So I'll suppress our global bonded contacts, and we can automatically go ahead and search the model for faces that are coincident. You see we've automatically found the faces that are touching and that we want to apply a bonded connection. And we'll exclude the end of the tube to the top of the bracket because that wouldn't be bonded with our weld scenario. And we exclude this one also and include the rest of our contact sets. So here we go. We have 4 sets of contacts, and this is going to be a little more accurate, and so we can rerun our analysis and see the effect that this has had on displacement. We see our displacement's gone up slightly, and then as we would expect, the mass of the model has stayed the same and stress has increased also. Now, this is one way to perform the analysis using solid contacts, but this part is relatively thin compared to its overall dimensions. So when we look closely at the section of the shell or the section of the tube, we see that this is something that we would more than likely want to mesh as a shell element. And then also we want to use a more efficient method for emulating our weld behavior. So with that, I'm going to go ahead and switch back to my initial model without the fillet. And I'm going to rename this Shells with Edge Welds. So the first thing I'm going to do is select the tube body and define this by shells. The shell is a two-dimensional element. We define the thickness, and it's better suited for thin geometry. And we're no longer going to need our global contact, so I can just delete this, and I'm going to use an edge weld connector. And we see the intersecting edge is automatically picked up. We can define whether it's on the inside or the outside. This is a single-sided fillet weld, and also the size of the electrode. And the great thing about using any type of connector in analysis is that we can do a strength check and look at the forces through the connector. And I can then just take my fixtures from my other analysis and drag them over. So we'll take my force and my fixture, drag that to the edge weld analysis, and then we'll also want to turn on the trend tracker here. And material properties. So SOLIDWORKS is going to let us know if we don't have everything ready to go. And we set our baseline with the trend tracker. And now I can look at my displacement values. So we're well over 2 millimeters. Nice thing about shell elements is I can adjust the thickness without having to change anything in the geometry. So let's change this to 3 millimeters thick and rerun. And we see now we're getting close to our target of 2 millimeters, but we can see which direction the stress is going. Obviously it's increasing. That's not the route I want to go. Let's go with a more efficient route, and that's keeping the tube at the same thickness, but let's increase the outer diameter of the tube. So I can go over into the CAD model. And let's go from 1 inch to 1 1/4 inches outer diameter. And then rerun the analysis and see what our results look like. So now we see that our mass is coming back down, our maximum stress still within allowable limits. But we see that we're hitting our deflection target of under 2 millimeters, and so the design looks effective. And then from here we could go and evaluate the fatigue life of the design.